away with the first one, a presentation from Margaret Glasscoe from the JPL NASA, advancing access to global flood modeling and alerting using the PDC disaster-aware platform and remote sensing technologies. So I stop sharing. Maggie, the floor is yours.
Great, thank you so much. Let me start sharing my screen. And can everybody see my screen?
Yes.
Okay, great, wonderful. Thank you so much for the opportunity to speak today, and good day to everybody. As Peter said, my presentation today is about advancing access to global flood modeling and alerting. And this project is a large project with a number of COIs, as are listed here on the title screen. And I'll jump right into it. As you know, probably, flooding is a frequent event responsible for significant impact worldwide. As of September 2020, there have already been 91 flooding events globally. And since 2000, on average, there have been 100 floods annually occurring worldwide that have caused about $10 billion US financial loss per annum. And this slide shows the flooding frequency per year across the continents and the flood damage in US billion dollars per year. And as you can see, this is a great global impact across the world. So the focus of our project includes 4 major components. It uses disaster aware, which is the PDC's open access global flooding alerting system for effective dissemination of flood risks and potential impacts to aid with emergency response. And central to the project is incorporation of flood model outputs and remote sensing derived products from multiple platforms to help with the mitigation of flood risk and increased resilience of impacted communities. The 4 main components are a model of models approach to help forecast severity at a global scale by integrating flood outputs from 2 simulation models. And I'll go into that specifically in this talk. But there are other 3 components to the project, which include inundation outputs from Earth observations that will validate the model of models, a machine learning based flood damage assessment that will generate impact outputs for vulnerable locations, and an end-to-end pipeline that integrates all 4 above mentioned components into the disaster aware platform. Oops. So there are 3 major tracks of the project, which I just mentioned. So there's track 1, which is the model of models approach. Track 2, which is the Earth observation-based flood extent extraction, and track 3, which is the machine learning-based damage assessment using Earth observation data. So today I'm going to focus on model of models approach because that is our global flood forecasting component of the project. The objectives of the model of models approach are fourfold, and the purpose is to deploy and develop this approach, integrating hydrodynamic models and remote sensing derived products for flood forecasting. So we integrate 2 globally operational flood forecasting models, Glowfass and GFMS. And we then classify flood severity and send alerts based on the severity level, similarly to the USGS pager severity alert for earthquakes. And we use the PDC disaster aware platform to do this. This then provides situational awareness information for impacted communities in near real time for response and recovery efforts. We then validate and calibrate these models using synthetic aperture radar and other Earth observation derived flood outputs. So this is the model components and weighting criteria. We use Glowfass and GFMS to get flood severity Glowfass has it in point regions and GFMS and raster. From then we get event identification severity. We take a watershed-based risk index and create a threshold-based flood output, flood-based output for incident hazards, and then we feed that into disaster aware. Down below, we see the weighting factors for each of the models. Glowfass has 20-year percent levels, 5-year percent levels, 2-year, and then they get alert level, medium, high, and severe, and then days until peak. The weighting factors for GFMS are total area, percent area, mean depth, max depth, and duration of flooding. So what exactly is the Watershed Risk Index for riverine score? This provides information for 16,000 basins, considers 9 event return periods, and incorporates the level of flooding protection, and then gives expected annual affected population. We use the Watershed Risk Index because we wanted to have a quantification of a level on which to base the alerts. And then for the two flood forecasting models, for GFMS, it uses real-time precipitation information from NASA Global Precipitation Mission, GPM, satellites, and implements a hydrologic runoff and routing model for flood detection. It's at a quasi-global scale and is implemented at an 8-degree lat-long grid. The following outputs generated at 3-hour intervals at a 0.125 degree grid resolution are used in the model of models. The size and area percent in a watershed impacted by a flood, depth above baseline, and duration of days. For Glowfass, it's a global hydrologic forecasting and monitoring system independent of administrative and political boundaries. It couples state-of-the-art weather forecasts with a hydrologic model to provide downstream countries with information on upstream river conditions, produces daily flood forecasts and monthly seasonal stream flow outlooks, and severity indicators are used daily for the model of models, probability of return period, 2, 5, and 20 years, alert peak level, and peak forecast in days. So how is this used in our system? So we had a case study in spring of this year for the flooding in Central and East Africa. The countries, particularly Kenya, Somalia, Sudan, South Sudan, and the Democratic Republic of Congo, experienced severe flooding this past spring as they had greater than normal rainfall occurring in their long rain season. So flooding in Africa led to exposure and risks to vulnerable populations and infrastructure. And oftentimes these risks are compounded by multiple associated events. Heavy rainfall causing both flooding and landslides. The disasters program at NASA, in fact, activated for research purposes for this event. And you can see what we did for this particular event at the following URL. Now, what we did for the riverine basins was to capture the watershed risk in terms of watches, warnings, and advisories. Now, the riverine basins that have no hatches or dots are not affected at all. But as you can see in some basins you have hatches, which are watches, dots, which are advisories, and slants, which are warnings. Now, the most severe of these are the watches, and the least of these are advisories. Now we have a comparison here of the model of models output and the disaster aware manual alerts for September 21st, 2020. As you can see, we have a number of alerts here that were indicated by the model of models outputs compared to disaster aware's alerts. And we have a fairly good alerting in comparison, but you'll see that in some cases there we have a better alerting than disaster aware. Just a little note on disaster aware, on the disaster aware platform. Disaster aware is maintained by the PDC, which is a University of Hawaii Applied Research Center. It provides multi-hazard warning and situational awareness information through mobile apps and web-based platforms. And the operational version is used by multiple national and international agencies, including the UN. It provides early warning alerts, risk and vulnerability, hazard impact estimation, and lists the critical needs. Now, the current capabilities of disaster aware lacks a global flood identification and alerting component and doesn't integrate remote sensing components to enable near real-time validation of simulated flood modeling results. This is the reason why the PDC approached us to work with them on this particular project. The use of remote sensing imagery to validate the near-time results of flood models incorporated into disaster aware will help them with situational awareness and impact estimation to quantify their disaster impacts. And the integration of these publicly available global flood modeling sources and remote sensing platforms will help them to create a robust and comprehensive platform for flood damage assessment and alerting that will help them with community resilience. So we see here that we have this sort of feedback loop here where we have the flood models to help with global flood identification and alerting, remote sensing that enables the near real-time validation of simulated flood results, which feeds into disaster aware, which is used for situational awareness and impact assessment, which leads to greater resilience, which includes integration of these components, which will create the robust and comprehensive platform, which will help with resilience. Right now, PDC has a platform for disaster aware that includes 7,000 users globally, and their free to use disaster alert app that has over 1.4 million users globally. And with that, I think that is the end of my presentation. So I can take questions in the chat and we'll be happy to participate in the discussion at the end of the rest of the discussion. So thank you very much.
Thank you, Margaret.